let's begin with quickly recalling what we did yesterday. So the higher points of yesterday are, we proved essentially that dense is dense actually. So in other words, if I have a set A which is dense and it's contained in some set, okay, which is, for which we don't know that whether it's dense or not, then we're going to say that A is dense in E, it's dense in E, and B contains A, then B will be also dense in E. This is what that we proved. And similar thing is true for the fundamental actually. So if A is a fundamental set in E, then B that contains A is also fundamental. So this was the key point that we just discussed yesterday. And the second point that we discussed yesterday, that if we have two maps which are linear and bounded from E into F, okay, in other words, they belongs to this space, calligraphic E from F, such that they agree with each other, on some dense subspace or a dense subset of E, or a fundamental subset of E. In other words, this A is dense or fundamental in E. Okay. So in other words, if two linear and bounded maps agree on a dense or a fundamental subset of E, then we can show, and we showed, that they also agree on whole of the domain that is E actually. And that's what make it the dense and the fundamental space is very important. Okay. This was the key thing that we proved. Then we proved a version of Vastus theorem, which in simple language said that linear polynomials over the interval A to B, the space of all linear polynomials on the interval A to B is dense in C. Okay. And then we ended our discussion ultimately at talking about a space that we say that that's a space of p-integrable functions with the complex support. Okay, so in other words, these functions are those functions. Okay, so these functions, this space and these functions are those functions which are kind of integrable, not necessarily continuous. Okay, but after a certain interval, they vanish actually. They have a kind of a complex. So outside a certain interval, they vanish. So they are integrable. In other words, you can compute area under these functions. Okay, but they have a complex support. In other words, after a certain time on both ends, the function vanishes. In other words, F is a space of p-integrable functions such that F has a complex support. Okay. So what we ended yesterday with an intention to show that this is space. Okay, what we know before this, we know that
CCR.
the CCR, in other words, the space of continuous and the compact support functions is dense in, so it's dense in CAB. Okay, it's dense in CAB. Okay. And so you can, okay, which is dense in LP of R actually. Okay. So this is no. Is it dense in CAB or C naught of R? It's dense in C naught of R. Okay. What we want to show essentially that this is space, and these, this space, like the space of all p-integrable functions with a compact support, these both are dense in LP of R. So these are kind of the vocab of things that you have to keep in mind. Why? Because you're going to see that there will be several operators, okay, for which we want to do kind of different investigations actually. Okay? And our investigations become much easier if we have kind of such conclusions over, the dense service spaces. Because once you have similar kind of conclusion or dense service spaces, you can extend it over, the whole space actually. And this is called essentially the density argument actually. So in other words, you want to do something in whole space, there is no need to do it, just do it on fundamental or a dense space or a subset actually. And that thing would be also true on, or can be true on the whole space actually. Okay? So this line of argument is called density argument. Okay? This line of argument is called density argument actually. So we'll prove some of the things through the density argument as well. Okay. So how we are going to prove essentially for this, if you remember, we discussed already that roughly intuitively how this is dense in basically. If you remember from the lecture before the yesterday's lecture, we discussed it, at least in case of L1 and L2, that how a function that is integrable, okay, over R can be approximated by a function which is continuous with the complex support actually. Okay, so the density of this is pretty much obvious actually. And let's show that this space is dense in LP of R. So this is what that we would like to do. For that, we'll like to do some preparations. Okay. I'd like to prove a lemma. Lemma says that this space of p-integrable functions with compact support is dense in LP of R. Okay, that is, if you pick an element which is p-integrable, okay, then there exists a sequence of functions. But I can be very specific about this sequence of function, that this sequence of function is going to be f multiplied by the indicator function of minus n to n. Okay, this sequence of function such that f and this sequence, okay, minus n to n goes to 0 in p norm as n goes to infinity. Okay. So kind of we are identifying the sequence. Okay, you don't need to find an abstract sequence, but there is a very complete sequence that you need need actually to approximate your given function. And yesterday we also discussed what precisely this pictorially mean actually. Imagine that I have some integrable function, okay, which is kind of defined over, I don't know how does it look like. It would look like this actually. So this is, a function, for example, in L1 of R, okay. Now what does this sequence is telling me, okay, that, okay, so what would be the meaning of, for example, okay, I can give this whole a name. This is Fn actually. So I'm asking from you, what is F1? So F1 is basically the F in the interval minus 1 to 1. Okay? So in other words, F1 is a function which is equal to F in the interval minus 1 to 1 and 0 outside. Okay? So in other words, in the interval minus 1 to minus 1, my F1 is equal to precisely this function actually. Okay? And 0 outside. And similarly, if I extend this, 2 to minus 2 to 2, so I'm going to have, a more better bit of this basic. And obviously, all these functions, if you see, they are integrable. So why F2 is integrable? Just think about it. So I can compute the area under this and this part, and it has a compact support. Why? Because outside the interval minus 2 to 2, it's 0. So that's an element precisely in this p-integrable functions with a compact support. Okay. So this is what that pictorially means. We can show it mathematically. Okay. Essentially, what you have to do is to simply compute the norm. Okay. It's pretty much obvious that why these elements must be there. Do I need to prove it? Prove it as well. You can show it easily. What I just need to show is that so the proof that I am writing roughly is for p equal to 2, but for any general p, okay, I should mention that what is p here. So the p is any number which is bigger than or equal to 1 and has to be infinity. So it's not infinity yet. Okay. This is sometimes called convex range. So I'm proving it for p equal to 2 essentially. But the rest of arguments would be very analogical here. Okay. So as you have f from L2 of R, okay, give me the reason that why this Fn must belongs to this, p-integrable function with a complex support. So it has a complex support. Okay, it has a complex support, and it's equal to, on each such interval, it's equal to f actually, which is integrable. So if this is integrable over whole R, so it must be integrable on the parts actually where the complex, where the function is defined at. So essentially, it's pretty much obvious that this must be true. You can essentially show it as well. So in general, this is true that f of n can be approximated, maybe what do you call, estimated by the norm of f actually. Okay, if this is true, then what? And you can. So do you agree that this must be true? Well, this is defined on whole R, and while this is defined on some part of it. So if this is true, then there is squares and there are integrals over R, the also going to be true. If this guy is finite, this guy is finite as well. Okay? So Fn belongs to N. Okay. We can also see pointwise actually. Okay? So if I have, for example, Fn of x actually. Okay? Fn of x. So Fn of x is equal to f of x when x is in the interval minus n to n, and it's 0 when you are outside minus n to n. When you're outside minus n to n. So what would be the difference Fn of x and f of x, okay, in general? So I can have two possibilities for x. So it could be outside minus n to n or inside minus n to n. Okay. So if it is outside minus n to n, the difference is 0. Okay. And if it, no.
f of x.
Okay. For outside the difference is f of x, and for inside the difference is 0. Which is less than or equal to mod f of x actually. What can we say? Okay. But obviously, okay. But obviously, as n gets bigger and bigger, even the distinction between Fn and f, when x is outside this minus n, like inside this interval minus n to n, is going to get to 0 as well. Agree?
Yes.
That this should be the case.
Outside 0 1.
Huh?
Outside interval 0
Then even inside interval is also going to be. So as n gets to minus infinity to infinity, okay, the interval gets bigger and bigger and bigger. There will be no difference between Fn of x and f of x essentially. This goes to 0. And what we can show, if this is true, then obviously as n goes to 0 at pointwise actually, then the key thing that we would like to show is that f of n and f in 2 norm and its square should go to 0 as well. Okay. So why this should go to 0? X and f of x, okay, over whole r, okay, should go to 0. Why it should go to 0? Because the integrand is going to 0. Okay, it's a less precise argument actually. There is a result which is in measure theory. I'm not going to use it, which says that if a sequence is pointwise converging and satisfies some condition, then their integrals are also going to converge to each other. Okay, but we have seen such results in real analysis that if integrand is 0, then the integral intuitively goes to 0. Okay, and this means that every element in f can be approximated by the functions in this space, which is space of the p-integrable functions with the complex support. Okay. So far we know two subspaces of the space of p-integrable function, which is, one is CC of R, space of continuous functions with a complex support, and the second is the space of p-integrable functions with a complex support. Okay. I'm not getting into proof of another fact. Okay, I mean, if you wish, you can read it for yourself, but it is worthwhile keeping that. So you see, when you are dealing with the, when you want to, for example, solve some of problems which involve, say, differential equations, or maybe, partial differential equations, but in infinite dimensional spaces like such in the spaces. Okay. So for the differential equation, say a second order differential equation, the solution has to satisfy roughly. I'm not talking precisely here, so I'm talking less precisely. For a second order differential equation, for example, a linear second order differential equations, what should be the key properties in the solution? So you want at least a C2 class function which satisfies that differential equation. So in other words, you want function to be continuous. You want function to be first and second order derivative, okay, to be what you call continuous. So if you want third order, differential equation, you need third order regularity basically. So you need more and more regularity of the solution actually. Now the trouble is that, for example, if I want to solve, so imagine that, I have a second order differential equation, but I am sitting in this space. Now, for example, I want to solve, roughly solve in inverted commas, a second order differential equation in LP spaces, for example, for some suitability. Okay? Then the density argument essentially tells me that if somehow I can solve this equation here, then the solution can be extended roughly. So I'm talking really less precise actually, so don't take these things that I'm saying at the moment as facts actually. So what I'm saying is just, to give you a bigger picture, an intuitive picture. So I want to solve an equation here, whose solutions are here, okay? Then it is sufficient to solve such an equation, the equation here actually. But the trouble is going to be that this only contains the continuous function. While for solving a second order differential equation, you need at least second order regularity, a regularity up to second order actually. So what we should do, we're going to say that, this dense space is good, but not good enough actually. Okay, not good enough for solving especially differential equation problems actually. We're going to see some of them. Okay, so here is a space that I'm introducing. Okay, so now I'm introducing the space C infinity. Okay, so what is C infinity? So C infinity is the space of the continuous function whose all derivatives are continuous as well. So it's an infinity class, what do you call? So we call the elements of such function, we say that it's a space of smooth functions. Smooth functions. That is, the functions, okay, in say LBR, for which f prime, whatever prime means, we don't have at the moment the meaning of prime, so we know prime in R, but what would be the meaning of the derivatives here actually? For this, probably we need to wait for the next chapter. Okay, so f double prime, and so on and so forth. So the derivatives of all order are continuous. Okay, so this is what the space of continuous over R. Over R, if you want to put an R here, are the interval basically. But here's the space, that is C infinity C of R. What does it mean?
Complete
So it's a
support.
space of all smooth functions, space of smooth functions with a complex support. Okay? So it has been shown in the next, what do you call, section, okay, which I'm leaving for you to read. I'm not making it mandatory, but I highly encourage you to read. That this is dense in LB of R. Okay? With respect to P naught. With respect to P. Okay. For solving practical problems in infinite dimensional spaces, this space is like a heaven. Because here you have smoothness up to any order you want that. Okay? So this space plays a beautiful role as well. Okay? So you have to keep this in essentially head. So I'm not getting into the proof of this. Proof is a readable proof, you can read it for yourself. So what in next part what I'm going to do, I'm going to apply some of these tools, use some of these tools for.
I was not getting this point. You said we can't solve this particular differential equation in this particular space. What does it mean to
It
solve?
means that for a solution of a second order differential equation, you need a function which is at least second order, which is, you need a function which is at least continuous up to second order actually, which is of C2 class actually. So if you don't have a function which is continuous up to second order, how you can find a basically solution of the problem. Okay. So as I said, I just gave you a rough sketch actually, so forget about that. I mean, it's fine if you don't get it at the moment. So I'm not being precise here. But we're going to be precise in the next part of the discussion. Okay, so for LP, keep these three essential spaces, that these are dense with respect to P norm in LP space. Okay, so whenever we need, we're going to use it. So I would like to apply some of these results and use some of these results for something that you might have learned recently. So have you done some Fourier transform?
No, sir.
You haven't done Fourier transform?
No.
You're not the Fourier series actually. You're not the Fourier transform. You're going to do transform.
In the next class, we are going to do.
Okay, you're going to do it in Fourier transform. So, what is Fourier series? What is Fourier series? It's okay. Give me a formula
For f.
for f of x. We need to be very precise. What should be the kind of f actually for which we can compute the Fourier series?
And what is this?
Can you? It must be periodic actually.
Even around.
It must be periodic actually. Even odd periodic, even odd. Then you can compute what do you call Fourier series of such a function. And what will be the formula for computing Fourier series roughly? So it's a sum. It's a kind of a sum going from somewhere to somewhere.
And
And if I write in, for example, exponential, have you seen the exponential form of this? So what's the exponential form of this? Cn e power
N pi.
n pi. Okay, so the formula is here. So it's equal to e power 2 pi iota and kt. Okay,
Our p.
and not kt but nt. Roughly this would be what do you call, the version of the Fourier series that you have learned actually. You can put it into such an exponential form.
T plus 1.
Huh?
T.
E.
T is a T.
Yes.
T from R.
Okay, so it must be x actually. Okay, it must be x.
X.
It must be x.
So from negative to positive.
So what's